video, we'll be talking about the importance of thermochemistry and also the application of Hess law in enthalpy change. But before we go to applications of Hess law, we need to understand the applications of thermochemistry. From the word thermochemistry, we can know that it's a combination of thermodynamics and chemistry. That you can just say is the thermodynamics of chemical reaction, or you can also say is the study of energy which results in chemical change or which happen in a physical reaction. So let's take this scenario as an example of thermochemistry. When we spoke about the study of energy, if we look at it very critically, we know that energy can be in form of chemical, can be in form of light, can be in form of sound. So we are studying that energy, and when there is release of energy, it's implying that there is a release of what? Heat. And heat flows from a hotter region to a cold region. Let's take this scenario for instance. We are looking at a system here. There is a release in heat to the surrounding, and when heat is being released to the surrounding, our heat becomes negative, and when the surrounding absorbs the heat coming out from the system, our heat becomes positive. So from this, we can also state that our internal energy is equals to, that is our heat plus work done. And we can also say that work done, which is equals to change, that is pressure times change in volume. This is just an introduction to thermochemistry. Our main focus today is the application of Hess law, because thermochemistry or Hess law is a derivative from thermochemistry. That is, Hess law is one of the laws of thermochemistry. And Hess law, when we are talking about Hess law, we are dealing with two reactions, trying to initiate them to become one reaction. Two reactions, bringing them together to initiate or form our overall reaction. And when Hess law happens, there is a release in enthalpy change. Let's take an example. When nitrogen reacts with hydrogen, 3 moles of hydrogen, to form ammonia, and we are giving our enthalpy change to be minus 92 kilojoule. Then another reaction, when water decomposes to give us hydrogen and oxygen with an enthalpy of change in enthalpy of plus 286 kilojoule, and our overall reaction, giving our overall reaction to be that is ammonia plus oxygen to give us nitrogen plus water. So we can see from this that this is our overall reaction. So from Hess law, we try making the two equations, that is these two equations, equation 1 and equation 2, to look like the overall reaction. That is every single way possible to make these two reactions look like our overall reaction. And this can be done by, first, one, considering the two reactions, the one that is not common between the two. If you check from these two reactions, hydrogen is common. Hydrogen is on the first reaction and it's also on the second reaction. But we need to consider nitrogen. If we check from here, nitrogen here, nitrogen is not common. Nitrogen is just once, appears only once in this reaction. And what I said something concerning Hess law. Hess law, we are trying to make the two reactions look like the overall reaction. So when trying to make these two reactions look like the overall reaction, from here we can see that nitrogen, for the overall reaction, nitrogen is on the product side, and for this one, nitrogen is on the reactant side. So what do we do? From reaction 1, what do? We try and reverse nitrogen to the product side, and when reversing any reactant to the product side, our enthalpy changes its sign. If it's minus, it changes to plus, and if it's plus, it changes to minus. So and not only do we reverse it, if you check from our overall reaction, there's a multiplication of 2 here. So to make this first reaction appear to be like our overall reaction, we need to also multiply it by 2. So it becomes, we are also reversing it, so it becomes 4 ammonia, then to form 2N2, that is for our nitrogen, plus 6H2. Then our change in enthalpy becomes what? 2 times 92 kilojoules. It also affects our change in enthalpy. This becomes our equation 3. Then let's go for the other reaction, the reaction 2, because we are all looking for a method to make it look like this overall reaction. That is the main thing we are trying to do now. So from this water, we have water decomposing to hydrogen and oxygen. So from this, if we check our overall reaction, our water is on the product side, and if we check our reaction, our water is on the reactant side. So what do we need to do? We need to reverse it. And I said earlier before that when reversing, our change in enthalpy, the sign changes. It affects our change in reaction. So not only reversing it, from our overall reaction, we can also see that there is a multiplication of 6 here. So we also need to multiply this reaction with by 6 rather. So when multiplying by 6 and also reversing it, it becomes 6H2 plus, when we add 6 there, it becomes 3 oxygen, then 6 molecules of water. Then our change in enthalpy becomes what? 6 times minus 286 kilojoules. I said it also affect it. So from here now, we can see that we can easily cut out some things that are not really necessary to get our overall reaction. Like this hydrogen, we can easily cut it out, and adding both reaction, we can see that when we add both the equation 3 and equation 4 from what we were given, we can easily get our overall reaction from there. Look at it here. 4 ammonia plus our oxygen, then we get our nitrogen, we also get our water. You see, from here now you can see that our desired result, we've gotten our desired result. So to easily get our change in enthalpy for our desired result, that is our overall reaction, because that is the main objective of solving this, getting our change in enthalpy for our overall reaction. So we can just easily do it since we've gotten it. So we can just write in it again. 4 ammonia plus 3 O2, and don't forget we added both reaction to get it. So we are going to add 2 times 92 plus 6 times minus 286 to get our overall reaction, and that should be very easy to get, which becomes 184. That is, when we times 2 times 92, we get 184. Then when we do 6 times minus 286, we get minus 1716. So the answer becomes 1532 kilojoules. That is our answer for this reaction. So from this now, let's quickly go to another example for further understanding. And this example, we will be considering 3 reactions. That is carbon plus oxygen, which is giving us our CO2. Then they give us our change in enthalpy to be what? To be minus 94 kilocal. We can use kilocal, we can use kilojoules, all are still units of energy. So we can the second reaction giving us hydrogen plus our oxygen, which gives us water. Our change in enthalpy for this one is minus 68.3 kilocal. So the last one we're giving us C2H4, that is ethane plus oxygen, that is a carbon reaction, that is burning, kind of burning reaction. So it produce CO2 plus water, and our change in enthalpy for this one is giving us minus 342 kilocal. So this should be easy to do. This should be very easy from the other one we did, the first exercise we just did. This should be able. And our overall reaction, we're giving our overall reaction. Our overall reaction was given to be 2C, that is carbon plus 2 hydrogen to form ethane, and we're asked to look for our change in enthalpy for our overall reaction. So what do we do from here now? Okay, since we're given carbon, hydrogen and ethane, and we from our first reaction we know that carbon is on the reactant side, so we can easily just multiply 2, so it becomes 2C plus 2 oxygen to form CO2. Then our delta H becomes what? Becomes 2 times, since we are not reversing it is still the same. We are not reversing anything, it's still the same. Then for our second reaction, it becomes 2H2 plus O2, because of we are multiplying it by 2, so we have what? 2H2O. Is also going to be the same thing because we are not reversing it, so the sign remains the same. Since we are not, it remains the same. Then for our last reaction, if you check, our ethane for our overall reaction is on the product side. So what do we do from here? We need to bring it to the product side. We need to carry it down to the product side. So that is, we are also reversing it, so it becomes 2CO2 plus 2H2. Then our ethane plus, you see, from here now we can see that it's becoming quite easy from here. So our becomes what? We are not, so only the sign changes, so it becomes plus 342 kilocal. So from here we can easily cancel what is needed to be cancelled. So our CO2 goes off, our oxygen goes off. When we add these two, it goes off. So adding 1, 2 and 3, adding 1, 2 and 3, we get what? 2C plus 2H2, which is giving us our what? Our ethane. So from this now, this is our desired result. So having this, we can easily get our answer from here. We can easily get our answer because we know that when we times for the first one, we will be getting what? We'll be getting minus 188. Then for the other one, we'll also be getting minus 136.6. Then the last one is plus, so it's plus 342, which amount to what? 17.4 kilocal. And this is our answer for the enthalpy change of this reaction. So from this now, I hope you understand enthalpy change from Hess law. This is CHE 222 Chemistry for Engineer 200 level second semester. Enjoy and have a nice day.